Global data transmission relies on optical infrastructure, but the physical hardware routing that light is reaching its structural limit. Industry-standard inorganic crystals, primarily lithium niobate, handle signal modulation today. But as data rates climb, these crystalline structures introduce steep signal degradation. Once transmission frequencies hit 40 GHz, lithium niobate requires excessive driving voltages, making it nearly impossible to efficiently integrate into dense photonic integrated circuits. To maintain speed without the voltage penalty, engineers are replacing rigid inorganic crystals with organic electro-optic polymers. This chart compares R33 tensor coefficients. Lithium niobate offers 32 picometers per volt, while polymers deliver nearly 300. Shifting to dielectric constants, polymers continue their advantage, operating highly efficiently in the 2.5 to 4 range, far below inorganic alternatives. High tensor coefficients guarantee a strong optical response to low electrical voltages, while low dielectric constants prevent the material from slowing down high-frequency electrical signals. Achieving these metrics requires a specific molecular orientation, forcing a bulk material to exhibit the Pockels effect, where the refractive index changes in direct proportion to an applied electric field. Once that molecular state is achieved, engineers face an equally difficult metrology challenge, proving the material works by accurately measuring those tensor coefficients down to the picometer. Scaling organic polymers into commercial photonics demands both thermodynamic control over molecular symmetry and rigorous, mathematically sound metrology to verify the results. This Taylor series expansion describes macroscopic polarization. The critical variable for the Pockels effect is chi sub 2. But if a material is centrosymmetric, looking identical in opposite directions, the chi sub 2 term completely zeroes out, leaving only a weak quadratic response. To prevent that mathematical collapse, chemists synthesize organic chromophores. These molecules use an electron donor and an electron acceptor, linked by a pi-electron bridge. This asymmetry creates a permanent directional dipole moment across the molecule. This diagram shows a guest-host polymer system. When standalone chromophores are mixed into a matrix like PMMA-DR1, they enter a disordered state. In a bulk solution, chromophore dipoles naturally pair up in antiparallel arrangements. Their polarities cancel each other out, reverting the bulk material back to a state of centrosymmetry. Engineers break this symmetry using a thermomechanical process called coronapoling. This graph plots the poling process. The polymer is heated to soften the matrix. Then, a massive electric field from a needle electrode forces the chromophore dipoles into alignment. The field remains active while cooling, permanently trapping them in a state of non-centrosymmetry. The strong macroscopic Pockels effect observed in these polymers does not exist in nature. It is an engineered state, forced into existence through precise thermodynamic and electrostatic manipulation. Once non-centrosymmetry is permanently established, the next step is extracting the exact values of the R13 and R33 tensor coefficients. Standard metrology, like Tangman reflection ellipsometry, struggles here. It ignores multiple internal reflections and uses indium tin oxide electrodes, which actively absorb light at the critical 1550 nanometer wavelength. This multi-beam interference pattern illustrates the metrological solution, a Fabry-Perot interferometer. The poled polymer is sandwiched between two highly reflective layers of spattered aluminum. Light entering the polymer bounces between these parallel interfaces, creating multiple transmitted and reflected rays. During testing, an alternating voltage is applied to the aluminum electrodes. Because the polymer is poled, this voltage modulates the material's refractive index. As the index shifts, the optical path length changes. This alters the phase difference of the internally reflected light, directly affecting whether the exiting beams interfere constructively or destructively. This block diagram outlines the characterization hardware. A helium neon laser fires into the sample, while a motor-controlled rotating stage alters the incident angle, sweeping through the transmission spectrum. The transmitted beam passes through a Wollaston prism, splitting into clean S and P polarized components that hit separate photodetectors. These photodetectors feed directly into a lock-in amplifier. This isolates precise optical variations occurring at the exact frequency of the applied voltage, stripping away background noise. This specific hardware arrangement is necessary to magnify invisible picometer-scale refractive index changes into macroscopic variations in light intensity that sensors can record. The interferometer produces a raw set of angle-dependent transmission intensities. Extracting the tensor coefficients from this data requires processing it through a rigorous mathematical model. This represents the Azam and Bashara 2x2 matrix formalism for tracking light through stratified media. The interface matrix I calculates transmission and reflection at every physical boundary. Meanwhile, the layer propagation matrix L calculates phase shifts as light travels through each material's thickness. Multiplying these matrices together yields the total propagation matrix, M. By fitting experimental transmission data to this theoretical model, the exact values of R13 and R33 emerge. By modeling the entire multi-layer stack mathematically, engineers account for every instance of absorption and multi-beam interference, producing a definitive tensor calculation. This flowchart details the software automation loop that drives the metrology setup. Custom LabVIEW software controls the motor steps while capturing the exact voltage output from the oscilloscope. To ensure accuracy, the software acts as a datekeeper. It calculates the standard deviation of the measured samples, automatically rejecting unstable phase shifts that lack sufficient modulation before any data is stored. We started with organic chemistry, physically forcing bulk polymers out of their natural centrosymmetry using an intense high-voltage corona pulling process. We then translated that molecular alignment into measurable data using Fabry-Perot interferometry and matrix mathematics. This waveguide model shows the final application for these characterized materials, Mach-Zehnder interferometers. When these specific polymers are integrated into the arms of an MZI modulator, their massive R33 coefficients achieve strong phase modulation using incredibly low drive voltages. Lower voltage requirements generate less heat and allow for faster optical switching. This enables integrated optical networks to bypass the 40 GHz physical barrier entirely. Scaling global data speeds relies heavily on discovering new organic materials, but proving those materials are viable requires a metrology pipeline that is physically and mathematically absolute.